Welcome everyone to the workshop. We're going to take another look at an example of power series representations of functions. And in this case, we're finally getting something a little bit more interesting. But we'll soon realize that it's hardly any more complicated than the examples we've already considered. And this can be observed by performing partial fractions, right? That is the actions. We can find the partial fraction decomposition as -1 over x plus 2 plus 1 over x minus 3. So I'm not going to go through the partial fraction decomposition of this rational expression. We're going to leave that for you to review using another video. I'm not sure that I have any posted at this time. I'm sure I will someday. So feel free to check out the video that I maybe have, or another video, or of course you can refer to the textbook for partial fraction decomposition. Okay, so let's see. If we have f of x is equal to this, then these look similar to the examples that we've considered already. So notice that -1 over x plus 2 can be written as, I can rewrite this as -1 over 2 minus a negative x. 2 plus x is the same as x plus 2. And this can be rewritten as multiplying the numerator and denominator by 1/2 would give me 1/2 divided by 1 minus, let's see here, multiplying by 1/2. Okay, so I guess I got a -1/2 times x. And now this I can recognize as the sum of a geometric series. So n equals 0 to infinity. And the a value is a -1/2. And the r value is -1/2 x. Raise that to the nth power. Now, if I wanted to, I could simplify this a little bit, which wouldn't be a bad idea. So let's just go ahead and say that this is the sum from n equals 0 to infinity. Here I have n factors of 1/2. Here I have an additional factor. That gives me n plus 1 factors of 1/2 times x to the n. Using this as my radius for the, well, I'm sorry, not the radius, but the r value for my geometric series, I noticed that I should have an interval of convergence. From -2 to +2. Excellent. So I just want to do the same thing now for this rational expression. 1 over x minus 3 can be rewritten as, let's see here, throw the negative up top, and I can write this as 3 minus x. And then I can pull out a factor of 3 from the numerator and denominator, or multiply the numerator and denominator by 1/3. However you want to think of that, it's fine. And we observe that that is -1/3 divided by 1 minus x over 3. Or you could say 1/3 x. That's fine too. But this is then the sum from n equals 0 to infinity of the a value, -1/3 times the r value of x over 3, or 1/3 x. Again, either way of writing it is fine. And here, I can simplify this just a little bit so we can observe it as being centered at 0, like we did right here. So this is the sum from n equals 0 to infinity of, here I have 1 factor of 1/3, here I have n factors. So I've got negative times 1/3 to the n plus 1 times x to the n. And again, using this for our r value in the geometric series, we can observe observe that we have a interval of convergence from -3 to +3. So what I want to do next is I want to combine these two power series representations for our two parts. Right? F is the sum of those two things, so I can write F as the sum of these two power series representations. Now what's very important here is that we actually have absolute convergence. If we don't have absolute convergence, then we can't rearrange terms, which would not allow us to simply combine these things. We did cover an example of that, or I do have a video that goes over an example of what can happen if we don't have absolute convergence. So rearranging the terms can be a problem, and to rearrange these two infinite series, or these two series together, we would have to put the first term with the first term, second term with the second term. In order to do that, we're rearranging the terms. All right, so this gives us f of x is equal to, let's see here, the sum from n equals 0 to infinity. And I can write these out separately and then combine them, and that would be fine. So I'll do that. -1 over 2 to the n plus 1 times x to the n plus the sum from n equals 0 to infinity of the negative of 1/3 to the n plus 1 times x to the n. So if I were to write out this entire series, if I were to expand it out and then expand this one, I would never be done writing this one out first of all, so I'd never get to that one, which kind of hints at this idea of having to rearrange the terms. If I want to write f of x simply as the sum from n equals 0 to infinity, I have to take the 0th term and put them together, the first term and put them together, to give me -1/2 to the n plus 1 minus 1/3 to the n plus 1 times x to the n. So that gives me a power series representation for f of x. Of course, we should consider, where does this converge? Well, this part converges from -2 to +2, and this part converges from -3 to +3. So I cannot say that f of x converges at 2.5. While this would converge, this would not. So I can only consider the common interval of convergence, or the common area in which these two representations converge. So we get an interval of convergence. Again, it's going to be the common values from the two individual intervals of convergence. Now this one is contained in that one, so it's just this interval here, from -2 to +2. All right. Yep, I want to say that's all I had to say about that. I think that there was another comment maybe rolling around in my head somewhere, but it's rolled off for now. So we'll leave it, and if I think of it later, maybe I'll add it as a comment to the end of this video. Otherwise, I look forward to seeing you guys again soon back here in the workshop.